All right, today we're looking at basic limit laws as well as continuity. So the first thing we want to look at is your basic limit laws. And this is really when you're manipulating limits and you're using algebra to evaluate limits, you use these all the time without really thinking about them. There are a few that I want to point out. There are a few that are going to be really obvious to you. The first one I want to point out is the product law. This law doesn't apply to other things or other things we'll use in the future, like integrals, derivatives, and so on. But if you have two functions multiplied together and you're looking at the limit as x approaches c, as long as the individual limits exist, then all you have to do to evaluate this limit is just find the two individual limits and multiply those together. This also works the same way with the quotient. That's what the quotient law. So as long as these two exist, and as long as this one has an extra piece, denominators can't be zero. So as long as the denominator isn't zero, then we, I didn't need that there, sorry. Then we can just evaluate each one and divide. You can also pull limits inside of roots, inside of rational exponents, and so on. Now here's an example of the way you would use the limit laws. You really just, later you're just going to do this naturally, but I'm going to write it out for you. One of the limit laws that we're given, I'm not quite sure if it's on this page, it's not, is that the limit as x approaches c of just x, so just that variable is just going to be equal to c. So then what we can do is we can take and we are going to use what we just learned about the limit laws. We're going to use the quotient rule. We're going to pull it inside of the root, and we're just going to evaluate it like this. So we're going to have the limit as w approaches 7 of w plus 2 plus 1. So I've used the product rule. No, sorry. I've used the addition rule. I've used the rule about pulling it inside roots, and I've used the quotient rule. I'm going to use these same three rules to write the problem in the denominator like this. The limit as w approaches 7 of w minus 3 minus 1. And now what I can do is I know that the limit as w approaches 7 of w is just 7. This is also just 7. So I can then just kind of plug and chug and see what I get. So this ends up being the square root of 7 plus 2 plus 1 all over the square root of 7 minus 3 minus 1. And you get 4 over 1. 4, 4. So I'm able to use the limit laws, knowing very little about limits and solving them algebraically or anything, and evaluate this limit. Now let's look at when the limit laws won't work. So let's do it this way. So I have this example right here. There we go. So looking at the limit as x approaches pi over 2 of x minus pi over 2 times tangent x. So if I wanted to apply the limit laws, what I'd probably try to do first is to apply the product rule. And then once I apply the product rule to this piece, then I can apply the addition rule or subtraction, because if I don't have a variable there, then the limit isn't going to affect it. So I could write it like this, of x minus pi over 2 times limit as x approaches pi over 2 tangent x. And now this is going to be pi over 2 minus pi over 2, which is 0. This thing right here, if you know what the graph of tangent looks like, it looks like this. I'll write it like this. So you have asymptotes at pi over 2 at every constant multiple of pi over 2. And so this limit doesn't exist. The limit from the left doesn't equal the limit from the right. So since this limit doesn't exist, then the product rule does not apply. So we'll manipulate these limit laws a lot when we start using continuity to evaluate limits, when we start using algebra and trigonometric identities and all those sorts of things. We're not going to sit here and work a bunch of examples like this because I don't really think that it's going to serve you a lot of good. I am really interested in you guys having a deep understanding of continuity and limits. So we're going to spend most of today's homework and examples working on continuity and limits. So here's the definition of continuous. It's continuous at a point. You always talk about continuity at a point. If you look at it over the interval, that means it has to be continuous at every point on the interval. But generally, you just look at a point. So this means it's going to be continuous at x equal a if, and we've seen this before, right? If this limit as x approaches a from the left is equal to the limit as x approaches a from the right. And we have this extra piece over there. And it has to equal to the function value, which is different. So the limit has to exist, and stand will exist and is equal to f of a. So you can also, in words, think about it like that. So that's how a function is continuous at a point. So let's talk about how it's not continuous at a point, just discontinuities. So here we have what's called a jump discontinuity because you're jumping from one value to another. This is called a whole or a removable. I don't know if there's an E there. We're going to pretend there is. Discontinuity. This, the limit exists, right? Because if we come from the left and we come from the right, we're approaching the same value, but it is not continuous. All right, here is an infinite discontinuity. Has another word called an asymptote, right? It's always a fun word to spell. We also have kind of a none of these. There's not a lot of functions that fit into this category, but if you have, say, a periodic function that's just going crazy close to a value and it's jumping all over the place, it's not approaching anything, then you can say that it's discontinuous, but it's not one of these jump, removable, infinite. And here's a good example. You can graph this on your calculator, zoom in really close to 0. No, that's not what it's supposed to be. Sorry. Sine of 1 over x. And we want to look at the limit as x approaches 0. So look around 0 as what happens to that function. It's pretty interesting. May not get a great picture on your calculator, but do what you can. So now we have these other two types of, no, sorry, say this. When we have a discontinuity, it can be what's called left continuous or it can be right continuous. And what this means is that, say this is 2 right here, then obviously we have a discontinuity at 2. This would be a jump discontinuity, but the function value is when we're coming from the left. F of A is defined, or f of 2 is defined. So this would be left continuous. So if as you're approaching from the left, the function value is defined on that interval, then it's going to be left continuous. If as you're approaching from the right, the function is defined on that interval, then it's going to be right continuous. So here's an example for you. So here we have at each point of discontinuity, we want to see whether the function is left or right continuous. So I know I have this whole list of functions that I know are continuous everywhere. One of them is polynomials. Every one of these are polynomials. So the only discontinuities I'm going to look at are going to be where it jumps. So when I jump from this function to that function, and when I jump from this function to that function. So at 0 and at 2. And then what I can do is I can evaluate each function at these points. I want to evaluate these two at 0. And first see if they are if it's discontinuous. It could be, and it happens sometimes, that these two functions are equal at 0, x cubed plus 1, and negative x plus 1. And if those two functions are equal at 0, then you don't have a discontinuity there. They're going to run right into each other. If there's a discontinuity there, then I want to see on what side does the function value lie. And the easiest way to do that is to, that's good. Oh, oops, no, sorry. Is to look at your inequality symbols. This one is less than or equal to. So if this were a discontinuity here between x cubed plus 1 and negative x plus 1, then this would be left continuous because I'm including 0 in the interval on the left side, on the x cubed plus 1 side, the less than side. If at 2 there was a discontinuity, then this would be right continuous because it's greater than or equal to. So that means as I'm approaching from the right, the values that are greater than 2, my function value is going to lie in that piece. So let's do a little algebra and see what we can come up with. So I first want to evaluate these two pieces at 0 and see if there's a discontinuity. So I'm going to take the first piece at x equals 0. So that's going to be 0 cubed plus 1, which is 1. And the second piece is going to be negative 0 plus 1, which is 1. So this is continuous because they are the same value. They're going to approach from the left and approach from the right, and then they're going to equal each other all at 1. Now let's try it 2. We have negative 2 plus 1. At x equal 2, we're looking at these two functions because they are jumping at 2. So negative 2 plus 1 is negative 1. That's going to be that piece right there. And then for the other one, this is going to be negative 2 squared plus 10 times 2 minus 15. And when I do that math, I get positive 1. So this is discontinuous. Discontinuity at x equal 2. So now I want to see where my inequality symbol lies. So my inequality, I'm less than on this middle piece. So that means that as I'm coming from the left, I am not including 2 on that piece of my graph. As I'm coming from the right, because of the greater than or equal to, then I'm including 2 on that. So this would be right continuous. And then I'm just going to say down here. Right continuous at x equal 2. So check the jumps. I would say, 0 and 2 are my jumps, and then look and see where that equal part is. If the equal part's on the left side, then it's going to be left continuous. If the equal part's on the right side, it's going to be right continuous. Now, these are always fun, I like these problems. Now we're going to see what values of a, b, and c do we need in order to make this function continuous. So in order for it to be continuous, these two things have to be equal at x equal negative 1. And then these two things have to be equal at x equal 1/2. So wherever the jump is, the y values have to be the same, and you'll end up with a smooth curve. It'll be kind of maybe a funny looking smooth curve, but we'll get a smooth curve. So what you want to do is you just want to set the first two pieces equal to each other. So I have x to the negative 1. I write that as 1 over x is equal to the second piece, ax plus b. And we want these two things to be equal where our jump is. So that's going to be at x equal to negative 1. So if we want these two things to be equal at negative 1, we just plug in negative 1. So we end up with negative 1 is equal to negative a plus b. So I have two variables, one equation. Probably not going to work for me for now. But I can now look at the second set of equations. So if I look up here, these two things need to be equal. You can see my circle, ax plus b, and the other x to the negative 1 need to be equal at 1/2 because that's where their jump is. And if they're equal, then we'll have a smooth curve. So at x equal 1/2, ax plus b needs to be equal to x to the negative 1, or 1 over x, at x equal 1/2. So now I'm going to plug in. So this is going to be a times 1/2 plus b is equal to 1 over 1/2. So then I end up with, when I simplify, 1/2 a plus b is equal to 2. So now I can do whatever I need to do. I have two equations and two variables. So I think what I did is I set up a system of equations and I eliminated. So I have, here's one equation, and there's my other equation. So let's solve this for b. So b is equal to negative 1 minus a. So I have 1/2 a, negative 1 minus a is equal to 2. So this is going to be, if I combine the 1/2 a and the negative a, I get negative 1/2 a. And then negative 1 minus 1/2 a is equal to 2. If I add 1 to both sides, I get 3. 1/2 a, I get 3, so negative 1/2 a is equal to 3. So then I get a is equal to negative 6. Doesn't seem right. Okay, so now let's try. So now I know a, I can just plug in and find b. So if a is negative 6, then b is going to be negative 7. So a is negative 6, b is negative 7. I really think I did something wrong. It's equal to 2. And so then b is equal to negative 1 minus b, and negative 1 plus a. Okay, I did. I'm glad I found my mistake. It's just algebra. Sorry. So if I solve this for b, then I get negative 1 plus a is equal to b. That's where my mistake is. Oh, if you something seems fishy, you should always go back and check it. So this gives me um, 3 halves a is equal to 3, which gives me that a is equal to 2. And then when I plug back in, I get that b is equal to 1. And these are the a and b that give me a continuous function. So this is super easy. Y'all been, this is a lot of times what you're going to think about when you're evaluating limits, or at least this is the first thing you're going to check. So if a function is continuous in a neighborhood around a, or you could really say it's continuous at a, then all the limit as x approaches a is just the function value. So you're just plugging in. So for roots, roots are going to be continuous everywhere that x is greater than 0. So here we're looking at limit as x approaches 2. So all you're going to do is plug in. So this is going to be the square root of 2 squared plus 3, which is the square root of 7. This is a really handy trick. Anytime you're evaluating limits, always check first to see if it's continuous at that point, because if it is, then just plug in. All right, I hope that this helped, and thanks so much.